Good morning all. Today's topic is fouling in heat exchangers. In this session we will discuss what is fouling, types of fouling in heat exchanger and their effects, review on overall heat transfer coefficient. We have already discussed overall heat transfer coefficient in one of the sessions. Here we will see how to estimate overall heat transfer coefficient for a heat exchanger with fouling. Then what is fouling factor and ultimately heat transfer rate. That is how to determine heat transfer rate in heat exchangers considering fouling. You might have seen deposits on the inner surface of kettles, teapots, or even in water bottles. This is a water heater with some deposits. You can also see a teapot with certain deposits on the inner surface. What is this and how this is formed? These are undesirable deposits on the surface due to continuous usage. This is generally known as fouling. In this session, we will deal with fouling pertaining to heat exchanger. What are the various sources and how to estimate the effect of fouling in heat transfer associated with a heat exchanger. In heat exchangers, fouling is the accumulation of unwanted deposits on heat transfer surfaces of a heat exchanger, and the deposits are known as foulant. These deposits cover the heat transfer surface area and acts as a barrier. Hence, these deposits impose additional resistance to heat transfer and consequently heat transfer rate is reduced. Now the question is how to estimate the thermal resistance offered by these deposits and thereby heat transfer. Here what we do is we will consider a heat transfer coefficient to these deposits known as scale heat transfer coefficient, and thermal resistance is estimated as we do in convective heat transfer. In convection, if we know the heat transfer coefficient H, then we can find out the thermal resistance. The same methodology is used here. We will discuss this in more detail later. Here you can see a shell and tube heat exchanger where we have certain deposits on the tube surfaces. The next is types of fouling. Based on the source, fouling can be classified into crystallization fouling, sedimentation fouling, chemical reaction fouling, corrosion fouling, biological fouling, and freeze fouling. The first one is crystallization fouling. This type of fouling is common when liquid handled by heat exchanger contains higher concentration of dissolved salts and minerals. At higher temperatures and pH values, the solubility of salt in solution decreases and consequently they form crystals and deposited on the surface. Calcium carbonate and calcium sulfate are the examples of salts that are deposited by crystallization. This process is also known as scaling. This can be controlled by adding chemicals such as acids or polyacrylates to water. The next is sedimentation fouling or particulate fouling. This is due to the deposition of suspended particles present in the fluid like dust, dirt, mud, etc. This type of fouling depends on velocity of flow, roughness of the surface, and size of the particulate present in the liquid. Sedimentation tendency decreases with increase in flow velocity and decrease in surface roughness and size of the particles. Sedimentation fouling can be controlled by using strainers for larger particles, maintaining higher flow velocities, and adding chemicals such as polyacrylates retards the tendency of sedimentation. The next is chemical reaction fouling. Chemical fouling is due to chemical reaction undergone by the fluid and deposition of the products formed from these chemical reactions. Normally, reactive organic fluids undergo decomposition or polymerization reactions when heated, and the resulted insoluble products are deposited on the surface. Carbonization is an example. That is, carbon deposits formed from organic fluids when subjected to high temperature surfaces. The next is corrosion fouling. This is due to the deposition formed from the chemical reaction between fluid and the heat exchanger surface. A thick layer with high thermal resistance is formed as a result of corrosion and is very common with water supply lines. Corrosion fouling is due to reactive nature of the fluid or impurities present in the fluid, and it can be reduced by using corrosion resistant materials like stainless steel, nickel alloys, etc. for the fabrication of heat exchangers. Biological fouling is due to the growth of living organisms like bacteria, fungi, algae, plants or animals on the surface of the heat exchanger. This figure shows biological fouling resulted from the growth of algae, which forms a barrier between the fluid and the heat transfer surface. Biological fouling can be checked by using chemical biocides like chlorine, bromine, etc. that kills or inhibit the growth of living organisms. The last one is freeze fouling. As the name implies, this fouling is due to the freezing or solidification of liquid when comes in contact with the cold heat transfer surface. This solid layer forms a barrier to heat transfer. Ice layer formed during the production of chilled water, wax deposits formed during the cooling of hydrocarbons are the examples for freeze fouling. As this occurs due to freezing, this fouling can be prevented by maintaining the temperature of the heat transfer surface higher than that of the freezing point of the liquid. Now let us see what are the main effects of fouling. As mentioned earlier, fouling creates a barrier between the fluid and heat transfer surface. Hence the thermal resistance is increased and ultimately heat transfer rate and performance of the heat exchanger is declined. In addition to thermal resistance offered by fouling, they also narrow down the flow passage, which leads to higher pumping loss. That is, more power is required for pumping fluid through the heat exchanger due to fouling. As fouling reduces performance, large heat transfer surface should be provided to meet the application, and consequently the capital cost increases. Fouling also leads to higher maintenance cost as regular cleaning, including mechanical or chemical treatments, are required to remove scales. In the analysis part, our ultimate aim is to determine the heat transfer rate of heat exchanger with fouling. In view of the same, we will review overall heat transfer coefficient and heat transfer rate associated with a hollow cylinder, which was already discussed. Consider a double pipe heat exchanger where hot fluid flows through the inner pipe and cold fluid flows through the annular space as shown. Here heat transfer takes place from the hot fluid to the cold fluid through the wall of the inner tube. So we consider the analysis of the heat transfer through the wall of the inner pipe by treating it as a hollow cylinder. So this figure represents the cross section of the inner tube. So this is a hollow cylinder with hot fluid inside and cold fluid outside. Let Ti and To be the temperatures of the inner and outer fluids, and Ri and Ro be the inner and outer radius of the cylinder. Here heat is convected from the hot fluid to the inner surface of the pipe with a heat transfer coefficient of Hi, and it is conducted through the pipe material and convected to the cold fluid with a heat transfer coefficient of Ho. So we have a convection inside and convection outside as well as a conduction through this wall. So the total resistance offered by this heat flow Q is the sum of two convective resistances and one conduction resistance. That is the convection taking place inside, the convection taking place outside, and the conduction that is taking place through the wall material. So if we consider the thermal circuit, it consists of three resistances. One convection resistance corresponding to inner surface, this one, and it is given by 1 by HIAI, and conduction resistance given by this one, and it is 1 by 2 pi LK Ro by Ri, and convection resistance corresponding to outer surface, this resistance given by 1 by HOAO. These resistances are in series, so the total resistance is the sum of all these resistances. We know that heat transfer rate is equal to temperature difference divided by total resistance encountered by the heat flow. Here, heat transfer takes place between the temperatures Ti and To. So heat transfer rate is given by this expression. This is the temperature difference and divided by total resistance. Total resistance is the sum of these three resistances, where Ai is given by this expression, that is the inner curved surface area, and AO is the outer curved surface area given by this expression. Substituting the values of Ai and AO in the equation, we will get this expression. Now, in this expression, if we take 2 pi RIL to the numerator, we will get this Q given by this particular expression. Now we have this expression. If we replace 2 pi RIL by AI, we can express Q in terms of AI by using this expression. Similarly, if you take 2 pi R0L to numerator, we can express Q by using this particular expression. Here also, if we replace 2 pi R0L by AO, then we can represent Q using this particular expression. So we can express Q in terms of AI using this expression and Q in terms of AO by using this expression. Next is overall heat transfer coefficient for hollow cylinder. We know that for combined conduction and convection, heat transfer Q can be expressed using this equation, where U is the overall heat transfer coefficient. For hollow cylinders, Q can be expressed in terms of inner area, where Ui is the overall heat transfer coefficient based on inner area. Q can be expressed in terms of outer area by using this expression, that is equation 2, where UO is the overall heat transfer coefficient based on outer area. We have already derived the expression for Q in terms of AI and Q in terms of AO given by equations 3 and 4 respectively. If we compare the expressions 1 and 3, we can get the expression for Ui, that is overall heat transfer coefficient based on inner surface area, by this expression. And if you compare equations 2 and 4, we can get the overall heat transfer coefficient corresponding to outer area UO by this expression. Now we will discuss how to include the effect of fouling to the hollow cylinder. This is the cross section of the inner pipe. Fouling may occur on both the inner and outer surfaces of this pipe. We assign heat transfer coefficients to the scales formed on the inner and outer surfaces, and corresponding thermal resistance is estimated. The heat transfer coefficient corresponding to scale formation is known as scale heat transfer coefficient. Let HIS be the heat transfer coefficient that represents scaling on the inner surface, and HOS is the heat transfer coefficient that represents scaling on the outer surface. This is the thermal circuit, and this is the expression for overall heat transfer coefficient based on inner surface area for a pipe without fouling. If we consider fouling in the inner surface, represented by the green circle, an additional resistance will appear in the circuit given by 1 by HIS AI. Similarly, if we consider fouling on the outer surface given by the red circle, an additional resistance appears on the circuit given by 1 by HOS AO. Now just identify how resistance on inner surface appear in equation number 5. Without fouling, there is only one resistance in the inner surface, this one, and it contributes to 1 by HI. But with fouling, there are two resistances on the inner surface, and this resistance contributes to 1 by HI as we saw in equation number 5. This additional resistance contributes to 1 by HIS. Similarly, for resistance on the outer surface, these are the two resistances on the outer surface with fouling. this resistance contributes to Ri by Ro into 1 by Ho, whereas this resistance contributes to Ri by Ro into 1 by Hos. So the overall heat transfer coefficient based on inner surface with fouling is given by equation number 6. Whereas for U0, without fouling, resistance on the inner surface, that is this resistance, contributes to this term, that is Ro by Ri into 1 by Hi. Whereas resistance on the outer surface, that is this resistance, contributes to 1 by Ho. So similarly for the case with fouling, this resistance on the inner surface contributes to Ro by Ri into 1 by Hi, and this resistance on the inner surface contributes to Ro by Ri into 1 by His. Whereas resistance on the outer surface, this resistance contributes to 1 by Ho, and this resistance contributes to 1 by Hos. So equation 8 is the expression for overall heat transfer coefficient based on outer area for a heat exchanger with fouling. Now we have the expression for overall heat transfer coefficient Ui and Uo for a pipe with fouling on both the surfaces, where HIS is the scale heat transfer coefficient for inner surface and HOS is the scale heat transfer coefficient for outer surface. The reciprocal of scale heat transfer coefficient is known as fouling factor. We can define fouling factor for both the surfaces. Fouling factor for inner surface RFI is equal to 1 by HIS, whereas fouling factor for outer surface RFO equal to 1 by HOS. The unit of fouling factor is meter square Kelvin per watt, which is the reciprocal of that of heat transfer coefficient. Overall heat transfer coefficient Ui and Uo can be represented in terms of fouling factors given by these expressions. And these equations are available in standard heat and mass transfer data books. Fouling factor or fouling resistance represents the resistance offered by fouling in a heat exchanger. In practice, fouling factors are determined experimentally by testing heat exchangers in both clean and fouled conditions. And the values of fouling factors published by TEMA, that is Tubular Exchanger Manufacturers Association, is available in standard heat exchanger data books. So far we have considered the system as a pipe with hot fluid inside and cold fluid outside. Now we will upgrade the system to a heat exchanger. We know that in a heat exchanger, temperature difference between the hot and cold fluid is not a constant. Instead, it varies along the length of the heat exchanger due to heat exchange. So for finding heat transfer rate associated with the heat exchanger, we use LMTD, that is logarithmic mean temperature difference. Thus, heat transfer rate is given by Q is equal to Ui AI theta m, which is equal to Uo Ao theta m. So if we know the overall heat transfer coefficient, area and LMTD, heat transfer rate associated with the heat exchanger with fouling can be determined. That is about fouling in heat exchangers. Thanks for watching. We'll meet in the next session. Till then, bye.